So for the second video in the Python tutorial, I want this video to focus on some of the functions of NumPy and how to navigate a couple of things. But first of all, if you downloaded Anaconda, then this is what it would look like. Okay, so when you open up your apps, if you're using Windows, come down to Anaconda, but then you've got several options here. The first, one, two, three, four, five, six, the first six are not what I use. Okay, now you can use these, and in fact, the Anaconda prompt and the Anaconda prompt, Anaconda 3, these are actually, in fact, all three of these are terminals very similar to what you would use if you were a Linux based operator. However, what the actual IDE, or the integrated development environment, that comes with Anaconda installed is the Spider IDE, and this is what the Spider IDE looks like. So here you would type in your code, here you would see output, and I've got it set up so that any of my plots and things would typically appear here, but they actually kind of create a new graphic. So for example, if I want to so once again, I'm going to create a column of numbers from 0 to 10, and let's populate this with 1,000 elements. Just because computation is cheap, we can do that very easily. And I want to plot the sine function and take the sine of each of those x elements, each individual x value, and and now if I run this program as is, all right, I know it's probably hard to see on your screen, and there's not much I can do about that, I don't believe. I might be able to, I don't know if this is going to make it any better. I don't think that moving it around is going to auto fit it in any way. So it is what it is. But if I plot this, I have it set up so that, oops, I need a comma right there. And so I've got it set up so that my plot appears as a separate window. And you'll notice that this is a very smooth calculation, right? This is a very smooth graph, as opposed to if I just put 10 points in here and ran the same code, you get a very choppy, jagged line, right? And that's because these are discrete points. And so because these are discrete points, if I try to connect them with a line, I have a first point here, second point here, third point here, fourth point here, and so on. Each point where there's an elbow is essentially where a point would be. And we can demonstrate that if we adjust this code like this. So this will give us both discrete points and connecting lines. And so these are the points in the X array. 0, 1.111, 2.2222, 3.3333, and so on that we saw in the previous video. And so the more elements that I give this, the smoother that is going to be. And so already at 100 elements, this is very smooth. And at 1,000 elements, it'll be smoother yet. In fact, you probably won't even be able to see the connecting lines. The dots will be so thick. Yes. And with these plots, you can zoom in, and I can get down to the level of seeing individual dots. Here we go. So here you can see the dots, and on top of that, you'll notice that these numbers up here in the corner change. So these numbers are keeping track of where my cursor is on my plot, right? So if I go home and I go to the point 0, 0, or at least very close to it, you'll notice those numbers are very small. And if I stay on the y equals 0 line as I go across here, x is increasing, but y is relatively constant at close to 0. Might bounce around a little bit because my mouse is moving up and down a little bit, but more or less. And then if I go this way, you can see the y value staying fairly constant. Or I'm sorry, the x value staying fairly constant and the y values adjusting, right? So you can get the coordinates of any given point on your plot, if you need it, from the numbers up in that window, right? But this is what the Spider environment looks like in case you want to download the Spider IDE from the Anaconda website. So that is that. But back to and I apologies for that. I have a lot of research code up, and this is asking me if I want to save changes to the code I just wrote. I don't really need to. And so we'll go back to the Python Baba website, and we will enlarge this so it's easier to see and read. And you'll notice here I just went to pythonbaba.com. And when you come to pythonbaba.com, let's do this from the ground up. If I come here, this is what you'll find. Okay. And so I want to scroll down, and the editor is not on the page automatically. I have to click on this Python code editor online. And when I do that, it's working, and here it comes. Okay, so there's a bit more junk here than there is in the extended URL that I showed you in the previous video, right? But we can actually get into a little bit about what some of these things are. First things first, you'll notice that this text is in green, and there is a pound sign in front of each of these. These are what are known as comments. And so anytime you want to write something like a note to either remind yourself of what you did or as notation for other people reading your code, you can comment, and one of the ways to comment is to start your line with a pound sign. And what that tells the editor is, this is just text. Do not do anything with this. So none of those lines that start with the pound sign are actually going to be read by the interpreter and the interpreter try to do something with them. It will just say, okay, I'm going to ignore this, but it's there for both your benefit and the benefit of anyone else who tries to read your code at a later point in time. But a couple of things. So first things first, when you just open up the interpreter as is, it automatically imports matplotlib.plyplot as PLT, the way that we did in the previous video. Pandas is a data science package. We won't get into much pandas, if at all, but do beware. We might, depending. But it is a very powerful package for handling large data sets, building databases and data frames, and then doing interesting calculations with the data in those. NumPy is again the numerical Python package, and SciPy, scientific Python, is a package that has a lot of high level mathematical functions that go beyond NumPy, and it also gets into some of the machine learning algorithms, some of the basic machine learning algorithms um, that form the basis of artificial intelligence applications, for example. That's not the only thing SciPy is for, but it's one of the more interesting things that SciPy is used for. Right, but it also has a lot of statistical packages in it as well. There are a number of libraries. For example, I'm an astronomer, and there are basic packages or functions, I should say, that astronomers like to use in a very specific way. And so some astronomers have written packages specifically for astronomers, and one of those is called AstroPy. And that basically has some of the same types of functionalities as either Pandas or SciPy, but implements them in a specific way that is useful for astronomy. So there's all sorts of packages, and they're constantly being released very, very quickly. But for the moment, NumPy, Matplotlib, Pandas, SciPy, those are all very, very standard packages. Now, we're not going to use SciPy for the moment, and we're not going to use Pandas. So, for example, some of the things in NumPy. All right, what are some of the functions in NumPy? Well, when you're working with NumPy, this is really where you're going to use things like your exponential function, logarithmic function, um, um, trigonometric functions, and so on. Now, here's a caveat. Remember, I said we import our libraries or packages in a specific way so we can reference them throughout our code. There's another package called math, and math has a lot of the same functions that NumPy does, but it even goes a little bit further in some cases. So, for example, in the trig functions, of course, you have sine, cosine, and tangent, but then you also have secant, cosecant, and cotangent. NumPy does not have an inherent function for secant, cosecant, and cotangent. So if you need those functions, you would just have to take the reciprocal of sine, cosine, or tangent, right? And so this is one reason why we do this, because if you have to use multiple packages that sometimes have overlapping functions, we want to know which library we're using to call a function so that A, the computer doesn't get mixed up, it knows where to draw your function from, and number two, also helps with debugging if you need to find what line of code is causing you trouble. The debugger will tell you the line that it's complaining about, and then if that line is a math line, then you'll be able to see if you're using NumPy or if you're using math or SciPy or whatever the case may be. Right, so that's why we import these this way. These are not the only way to import these, and I'll show you another way here shortly. But for the moment, let's just dive right in. Python is a very powerful computer. Okay, Python is a very powerful computer. So first things first, we've already looked at how to create an array. But that's not the only way to create an array. Okay. In fact, there's another type of function in NumPy called arange, and it differs from linspace. And something I didn't mention in the last video, but linspace is basically I don't know if this is exactly correct or not, but I think the phrase is short for linear space. So basically, a string of numbers, right? But if I want to um, create the same type of thing, a string of numbers evenly spaced, as an independent variable in a calculation, there's another way to do that, and that is with the arange function. Okay? And the difference here is you start by specifying your starting and end points, but here, instead of specifying the total numbers in the list you want to use, here you can specify the increment that you want to use. And so this actually takes a little bit less thought process in many cases, because if you know you just need the list of the first 10 integers, including 0, you can just type a 1 here. And this will give you a list of numbers. And one more thing, I should also mention this. This is actually maybe one of the things that I should have started with in the previous video. But we're using the version of Python called Python 3. Okay? I'm not sure if Python Baba is using 3.7, 3.8, or 3.9. But if you download Anaconda right now, chances are you'll get either 3.8 or 3.9. And basically what this means is that, so Python is an open sourceware code. And so developers who work on the back end can go in and modify things. And when the community essentially agrees on a valid change, that change gets updated into the base source code and gets released as a new version. Now, I don't think that they release new versions just for one or two minor changes. But one of the changes from Python 2 to Python 3 is how the print function works. Before, if I wanted to print something, all I had to do was call the print function and then use parentheses if I wanted to say hello world, and that would work. But here it doesn't. So it doesn't like that syntax. So the syntax in Python 3 is to put your thing that you're printing enclosed in parentheses right next to the print command, right? And oops. When you have text, it doesn't know how to interpret the text unless you enclose it in quotes, and that tells the computer that this isn't math, it's just a string of letters, and just to print that string of letters. So this is how you print in Python 3. But if I just want to print my mathematical variable x, I want to see what this list of numbers looks like and make sure that it's what I want, I don't have to enclose mathematical variables in quotes. And as you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is another subtle difference between linspace and arange. This number doesn't necessarily represent the endpoint. This represents the total number of elements in your list of numbers. Okay. So you're trading either knowing your end and or both endpoints and the total number of values that you want in linspace, for knowing one endpoint, knowing the total number that you want, and knowing the increment with arange, right? So if I actually want the numbers 1 through 10, I need an 11 right there. And there we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now this is an array that I can do some math with as an independent variable if I want to. So, for example, we can once again take the sign of this and we can plot this. Ooh. Getting happy fingers there. And there it is. And once again, because of the small number of values in my list that I'm calculating the sign from, it looks rather choppy. But there it is, right? Now, let's kind of go back from the beginning, right? And look at the difference between importing NumPy this way and the other way that you can import either NumPy or Matplotlib or what have you. Okay, so let's back out of these. And if you need, sometimes I've seen some code written like this. From NumPy import, and then based on the individual packages within NumPy that you need, you can import specific things. If you put a star right here, what this tells the computer is to basically import everything from NumPy, right? Import everything from NumPy. And when you import NumPy this way, you don't need to put that NP in front of your functions that you're drawing from the NumPy library. So this would be used if you need to do a really quick programming thing, maybe for a homework assignment, and you just need to program something quick. No one else necessarily needs to see it, and you just want to write a quick thing. And you also have to know that the thing you need to do is in the NumPy package, right? But for example, if I just wanted to calculate let's do this, okay, just for the sake of example. So I'm going to define x to be a set variable here. So what I'm doing is I'm binding x to be a variable or a set value. Okay, so x is my variable, and I'm binding that variable to the value of 0.4. So now, until I write x equals something again, the code will always interpret anywhere there's an x as the value 0.4. And let's say that I want to take the sign of 0.4. Okay. So now I'm doing the same thing with y. I'm taking the value of the sign of 0.4. The sign of 0.4 is just a number, and I'm binding that number to the variable y. So this is different from the arange or linspace functions, because those are arrays of numbers, not just individual numbers, right? But you can do interesting math with lists of numbers, just as you can single numbers, but sometimes you just want to use single numbers, and this is how you do it. And this is effectively binding a variable to a value, right? And so I want to know what the value of the sign of 0.4 is. And it gives me a value. Now notice, I don't have to have the NP in front of sign here, but if I import NumPy as NP, this code will not work. Okay? It doesn't know how to interpret sign by itself. Because I've imported the NumPy package as a given designation, it doesn't know, the computer does not know what sign means. It doesn't know to look in the NumPy package for sign unless I tell it to. So that is what this is. A second note, okay? A second note. Python computes trig functions, assuming angles are radians. So if you go into your calculator and your calculator's in degree mode and you punch in the sign of 0.4, you will not get 0.389. Okay? If you're in degrees, you will not get 0.389. That being said, if you change your calculator to radian mode, then you'll get the right answer. Okay, so anytime you are going to do a calculation, okay, anytime you're going to do a calculation, you want your value to be in radians ultimately when the computer makes the calculation or does the calculation. Okay. So what are some other basic functions in Python? Okay. Or in the NUMPY package particularly. So for example, and one thing you'll end up doing if you code is you'll spend a lot of time Googling. If you end up becoming a coder at any level, whether it's a professional developer or whether in natural sciences, you will be spending a lot of time Googling things. So for example, I want to know what the natural log function looks like. And so I'm just going to Google, and the first website that comes up is from the official NUMPY website that has the official manual with it. So what this is telling me is that the natural logarithm is just given as log. Okay, so what numpy.log means is that if I don't import numpy as np, and I don't just simply import all of the functions of numpy, I can import numpy as numpy, and whatever I import numpy as, if I use this syntax, import numpy as whatever this is, that's what would go here. Okay, so I could import numpy as numpy. Oop. And now my code won't work again. Okay, so I would have to put the entire thing here. Okay. Oh, and so when you look at this documentation, this numpy dot is just assuming that you have imported numpy as itself instead of an abbreviation or something like that. But at the end of the day, what that means is that this log is what I want. So if I want to take the log of x, and let's go back to this being np. Ooh. Okay, so it didn't complain at me, and I want to print this. And it gives me the natural log of 0.4. If I want the base 10 log, If I remember right, you just have to put the 10 there, and it gives me the value of the base 10, right? Um, and so you can do pretty much any function. So if I come back here and I Google what functions does NUMPY have? Okay, so if I come back here and talk about the mathematical functions, it's got sine, cosine, tan. Um, it does have the inverse trig functions, but does not have the secant, cosecant, and cotangent. Um, you can calculate if you know the first two legs of a right triangle. You can use the hypot function to give the hypotenuse. And you have the hyperbolic functions. You can round to a specific decimal if you don't want to keep all of the strings of your decimals. There's different ways you can round. You can now notice that this says return the product of an array of elements over a given axis. So this is not just taking the product of two numbers. Okay, this is going to give you the product of an entire array, or the elements within that array. The sum function is a very useful function. This just basically says, okay, I have an array and I want to add it all up. So, for example, here is my linspace. And once again, it's just a column of 1,000 numbers from 0 to 10. If I want this to be terribly evenly spaced, actually, let's just do 100. Let's just do 100. And let's just print this before we go any further. Okay, so you'll notice that there are now 100 elements in this list. And if I use 101, the numbers will be much cleaner, right? Because now I'm in increments of 0.1 from 0 to 10. And so what if I want to just know what the value of all these numbers added up is? There's a number of different ways I can do this. I can bind it to a variable. And then I can print that variable. Okay. And so if I take the numbers from 0 to 100 and add them all up, I will get 505. And as a matter of fact, if I take the value of the numbers 0 to 100, I should get 5,050. And sure enough, we do. Or if you can skip this intermediary step if you say, I just want to print what the sum of these values is, right? Now, it can get a little cumbersome. If you have a really big mathematical expression, it's often easier to bind that into variables and then just print that variable. But you can print the mathematical function directly if you so choose. Okay? Now, here is a very nitty-gritty point, but it's one that needs to be made. There are many different types of numbers in Python. So, for example, let's say I want to write the number 1. I want to use the number 1, but I want to use it in multiple ways. I'm going to write X and Y one without anything else, and one with a period. And I'm going to print both of these values. And you can print multiple things at a time if they're separated by a comma. So this is telling Python to print X and then print Y. And notice what the output is. Okay? Here I have 1, and here is 1.0. The difference between these is there's something else I can do, and that is I want to know the type of number that X is. And it comes back and says, okay, when we say what type is something, that's called a class. And it gives me int, which means integer. So this is being interpreted as an integer. So X is an integer. Integers are literally just that number. Okay? However, if I print type Y, this comes back as float. When you put the decimal here, this number is no longer just 1. It is 1.0. Technically, it's 1.00000000000. Okay, and so on for 16 zeros. 16-point floating number is the most common. And so what this means is that this number is now more computationally sophisticated. Okay, I can do interesting math with, and most of the computation that you'll do is with floating point numbers, because floating point numbers are where you handle your decimals. Integers will not handle decimals. So for example, if I want to take 2 and I want to divide it by 3 and I just use integers, and I say, okay, I want to print X divided by Y, 2 divided by 3. Now, if you plug this into your calculator, you'll get 0.66666666666, etc. And here, we do get this. So this must be new in Python 3, because in Python 2, this was not the case. So Python 3 is smarter than Python 2. I haven't actually experimented with the integers, so this is really good. You would get the value of it was either 1 or 0. I think it was 0, because it would always round down. It would go downward to the nearest integer. So this is valuable. But in any case, when you include the dot, okay, that tells the computer to treat this as a floating point number, which is most often what we're going to want to use. And so, now, what if I wanted to use Python as a fairly sophisticated computer, right? Now, remember, Newton's universal law of gravitation. So I'm going to write a little program that is going to compute the value of the force between two objects if I know their masses and their distance. So first things first, let's say the first mass is going to equal, let's say, 5 kilograms, and the other mass is going to equal 5 kilograms, and the distance between them is going to equal 1 meter. Okay, so one thing I can do is I can program this entire equation, Newton's entire equation, into one essential calculation of code and say, okay, this is going to be 6.67, and this is, remember, times 10 to the negative 11, right? And so this is Newton's universal constant, and this is going to be times the two masses divided by the distance between them squared, right? And I want to print that function, right? This is going to be a really small number, right? Because if I just have essentially two bowling balls a meter apart, the gravitational force is not strong enough to overcome the friction of the floor or shelf that they're on, and they don't attract each other. Nothing really interesting happens. So this shouldn't be surprising that this is a small number. But especially when you have lots of variables and terms in your equations, using Python as a calculator this way, just as a brute force calculator, can get a little bit cumbersome. A slightly more sophisticated way of doing things is to bind each thing to a given variable. So I'm going to bind 6.67 times 10 to the negative 11 to the value for g, and I'm going to say this is in MKS, or meters, kilograms, seconds system. Okay, and I'm going to say M1 is 5.0, and this is in kilograms. M2 is going to be also equal to 5. And notice that I'm commenting as I go. And R is going to be equal to in meters. Now, if you recall, the units on and perhaps I should write this in newtons times meters squared per kilogram squared in the MKS system. Maybe that's a better way of describing that, right? So these are the units on G, and it's in the MKS system, and these are the values in units on my masses and their distance. And so now this is a much cleaner equation, and something that is much easier to modify. If I want to change the values of my masses or my distance, all I have to do is change these one at a time without going into a really big expression and making sure that I didn't accidentally delete a parenthesis or a multiplication sign. And especially since you have powers being raised via two multiplication signs, if you accidentally erase one of those and then it interprets things as multiplication instead of exponentiation, things can get pretty bad pretty quickly. So this is just a cleaner way of doing things. And now if I say print f, then it should give me the exact same number, 1.6675 times 10 to the negative 9. But notice now that it didn't give me 1.6675. It gave me 1.667499999999. This is because partially due to the way floating point numbers are used in calculations, there's always going to be a slight rounding error. Now, in our case, the error, right? In our case, the error is 0.0, and there's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Our error is that. And if you want to make a federal case out of that amount of error, then I invite you to. Okay, that is more than enough for any of the calculations we are going to do in this class and anything that you would be asked to do on any of these extra credit assignments. But do be aware that that error is there. If you do a simulation over a long period of time, it does not matter. There will always start to be some computational error that creeps in. So this is something that we don't have to worry about for this particular type of calculation, but we do have to be very judicious later on when we actually start to build simulations. Okay? Um, and just for kicks and giggles, let's actually calculate what the force between the Earth and the Sun is. So the Sun is effectively 2 times 10 to the 30th. The Sun is 5.98 times 10 to the 24th. Oop. And they are separated by 1.5 times 10 to the 11 meters. Okay. And what is the force between the Earth and the Sun? The force between the Earth and the Sun is astronomically large comparatively. Okay. And if you recall, gravity does work really well at large scales when you get down to the size of humans and rocks and things like that. Electromagnetic forces and electrostatic forces are stronger. So that's why you're able to stand up and not be crushed down to the surface of the Earth by Earth's gravity. It's why when you rub your head with a balloon and your hair stands up, the electrical repulsion is overcoming the entire gravitational pull of the Earth, right? But at large scales, gravity is really, really, really strong comparatively. Now, gravity is always there, right? Gravity is always there. But at small scales, the electric forces are just simply much stronger. And that's a fact that we're going to use throughout the semester when we do our work. So coming back here to the functions, there are just simply a lot of functions. And we're not going to get into all of them by any stretch, okay? But I will mention sine, cosine, and tangent. We may get into arc, sine, arc, or the inverse functions. If you need to convert between radians and degrees, it's also really simple to just type in, if you have a value in degrees, it's really simple to type in that value times pi divided by 180 and turn it into a radian measure, for example. We've already talked about the sum, and so there is a function called trapz, and we will actually code from scratch a function called trapz from scratch and actually show you kind of how to numerically integrate things, right? Because numerical integration is very, very important. Most functions are not integratable analytically. They don't have an elementary solution. So most of the time when you run into an integral in higher level mathematics, if you need to solve it, you'll have to do it computationally. There are multiple techniques. The trapezoid rule is one of the simplest, most efficient, and in many cases when you have a decent range and a large number of values, discrete values that you can integrate over, it is quite accurate. So that's also one thing to keep in mind, but we will show you how to do it from scratch. If you need the exponential function, e to the something, okay? So for example, if I want to just print np.exp to the 1, right? So it'll print my force back out again, but then it'll also print this new value. And remember that the exponential value is 2.793 blah 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 blah, whatever it may be. I forget all of the string of numbers. 2.71828 1828. And if you have a small calculator and you just see this, you might be tempted to think that this is a repeating number, but it's really not. The exponential number is not a rational number, and it does not repeat. It just is a coincidence that this first string of numbers kind of looks like it repeats a little bit. But in any case, if I need to square the exponential number, then that's e squared. If I need to take it to the negative, then I can do that, and so on, right? And they're just, a treasure trove of if you get into higher level science, this is going to be a very, very, very necessary one, right? Very, very necessary one. This basically tells you what the maximum value in an array is. So if you do a calculation, let's say you have an independent variable array of times, and you do an experimental data set on or an experiment, and you gather experimental data on the positions of a particle, or toy truck or whatever you might be tracking. And you feed that into two arrays, your times and your positions, and you want to know what the maximum position the object achieved in your coordinate system. You can use the maximum function and get that. Or you can find the minimum, right? You can find the minimum. And square root function is right here. Or you can take things... you can do square roots by taking things to the 0.5 power, or you can use the square root function, which is a perfectly fine thing to do. Do we have the absolute value somewhere? You should be able to find the absolute value. Yes, calculate the absolute value. So if you need to program a percent error calculation, for example, you would use the absolute function. And in fact, we can do an example of that. So suppose we know G theoretical is equal to 9.8. And let's say you measured G in the lab to be something like 9.2, right? And I want to do a percent error calculation. When you have a character that starts out in pink, you may not want to use that character. You may want to find another way around that. So I'm going to call this new variable PE, and I'll make a comment here that this is going to stand for percent error. But if I just did this, the percent sign means something else, and it won't like that. So I can't create a variable in this fashion. I need to use a different syntax. So we'll just call it PE for percent error. And remember that percent error is the absolute value between your measured and your theoretical. And if you really, this is almost a glutton for punishment, because I'm typing in a lot of things. It's easy to make mistakes. You would generally want to shorten these, like maybe GT, for G theoretical and GM for G measured, and make a comment. And measured value in the experiment, and so then I would have GT, or and GM, and that just cleans this up a little bit. And remember that that is divided by G theoretical, and all of that is multiplied by 100. And so this calculates the percent error. Right? And if I want to just double check that I've got my syntax correct for how to use that function, I come back here and say, okay, absolute. And I believe this should work, right? I believe this should work. If it wants to complain, yeah. And if you click on any of these, it should oh, that's because this is not the function I was thinking of. This has to work on an array, not two values. That is my mistake. I apologize. Actually, what is the syntax for that? I forget it off the top of my head. Oh, wait a minute. Wait just a minute. Will this work? Because you have to put the mathematical function in there. Okay, yeah. So you put the mathematical function in there, not a comma, and say, okay, I want to take the absolute value between these. You have to tell it what to do. You have to tell it that you're taking the difference between those two values. And so that should work. Yeah. And so the difference between those two measured values is 6.12%. And remember, when you see this long string of numbers, it's in your best interest to judiciously round, right? You want to judiciously round these values so that way you're not taking strings and strings and strings of numbers when they aren't necessary, nor do they physically mean anything after a certain point, right? And in general, you have two sig figs here, so I should really only keep two sig figs here. So I would report that the percent error right? And if you wanted to, you could come back up here and use one of the rounding round given a number of decimals, right? And if I'm interpreting this correctly, what we would say is print np.round pe comma 1, and that is telling the interpreter to round the PE calculation to one decimal. And I think this is the right syntax. Yes, 6.1. So, there we have it. Okay, so I will leave that here. This video is a little bit longer than what I wanted it to be, but this does hopefully give you a sense of some of the things that you can do calculator wise. Um, and this will be very important moving forward as we go into further investigations. All right. If you stuck with me this far, I really, really hope you found this useful. If you're going into the hard sciences, I cannot stress enough, whether it's through these tutorials or learning on your own or taking official computer science courses, learn a language. I would highly recommend Python if you're going into engineering or physics or astronomy, or even physical chemistry. And we will leave that here and we will talk to you later. All right. Have a good one.